Well, I have prepared about 3 or 4 hours worth of introduction, which is not enough time. I don't know where to begin. Uh, Sandu I call him a force of nature. He is something completely unique. I'll never forget. I started doing my PhD with Yakir in Boston, and at that same time, Abner Shimoni gave Sandu a postdoc, and I think Sandu. You were still. It was the HP, right? I think it was an HP Bristol setup at that time, right?
No. That was when I was just a postdoc.
And, that's right. That's right.
I had nothing else.
And he, I mean, Sandu, for everybody who was working with Yakir, Sandu was always the go-to person, always. Like, Sandu, can you explain this to me? I'm still bashing my head up against the wall with this. And so he was always so generous, and I always believe he's the best speaker. He gives, and Lev, of course. Now, Lev, that you joined us, of course, you're the best speaker, right?
No pressure. No pressure.
But of course, Yakir was Sandu's PhD advisor. After that stint in Boston as a postdoc of Abner Shimoni, and of course, Yakir was in Boston at the same time. I remember this famous paper you wrote honoring Abner with Daniel Rohrlich. It's become known as the Popescu Rohrlich boxes, which has been just incredibly prolific. And around that same time, most of what Sandu was doing was foundations work. You have to remember, this is 1990, 91, 92, in that area. And I remember Sandu was thinking of branching out into quantum information theory. And he was debating it in his mind. And for me, it was like, of course you should do it. And very quickly, he started writing some of the seminal papers in this field. I mean, the papers that actually turned quantum information science into a science. So the famous distillation paper, which is basically that's the initiation of how we even understand how to quantify the resources in all of our quantum technologies. This is just the beginning. Sandu, I've completely lost track of how many papers you've written, but every one of them is an absolute gem. Every time a new paper comes out, I can't wait to read it. There's just a FYI, there's a famous paradox that actually goes way back to that 1989, 1990, called the photon in a box, which is a situation where using one of Yakir's favorite tricks, pre and post selection, you can take a single, say, infrared photon and apparently get a much higher energy photon out of it. And this has been a favorite topic of debate for 30 some years. The first fascinating article on that came out a few years ago in PNAS, and now the sequel, the resolution, is now coming out in PNAS. So everybody stay tuned for that one. That's going to be really fantastic. And with respect to prizes, I've also lost track of all of the prizes. I mean, Sandu won the Dirac Medal. He was, a couple years ago, he was one of the couple people out of 2.5 billion in the Commonwealth who was invited to join the Royal Society, the oldest, scientific society in the world. So if you have time, you should ask him about that. That was fun, signing his name in the same book as Sir Isaac Newton and so on and so forth. And many other prizes as well. So it is really, and Sandu has been so generous over the many, many years and decades, giving us one wonderful talk after another. And we record these, and I think, frankly, I think the whole world benefits from your talk, Sandu. So thank you so much for doing this. We're really excited to have you.
Well, always it's a pleasure. The pleasure is not as big as it is being there in person and meeting with all of you. But let's hope that the pandemic will soon be over and transatlantic flights will be not as dangerous as the moment. So let's hope for the good times. Thank you, Jeff, also for filling the time by saying so many things and allowing me to rotate so many papers here. So many.
I can always fill time.
In any case, yes. What I would like to talk today is about this dynamic Cheshire Cat effect and implication for counterfactual communication. And that is a paper with Aharonov and Eli Cohen. So, you know, there are so many effects that deal with non-locality and so on that are investigated lately. When I say lately, perhaps the last 20 years in foundations of quantum mechanics. But most of them are focusing on the kinematic part, I would say. So they look at Bell inequalities, entanglement, and so on. Things that depend only on the fact that the space of states of quantum mechanics is a Hilbert space, and you know the postulates of measurement and so on. But much fewer dynamical effects have been considered. On the other hand, well, Yakir is famous for looking at dynamical effects like the Aharonov bomb effect and so on. So today I would like to present another of these dynamical effects. So here it is the measurement. Here is the experiment. The experiment is deceptively simple, and this is the experiment that I will discuss. So what do we have here? Here I have a box, and there is, in this box, I have here on the left-hand side, just an ordinary wall. In the middle, I have a partition that is mostly reflective, and the transmission amplitude is epsilon, that I will take to be equal, well, I see here 1 over n, probably I would say for simplicity, pi over n, with n very large. So this one is mostly reflecting and very little transmitting. Now, I have a particle here that moves inside this cavity, and the particle also has a spin. And what I do, I prepare the spin in an up z state. Okay. Now I can take the time such and the particle heavy enough such that during this entire experiment, I will the particle will barely spread the wave packet. That I can do if I take the time short enough and the particle heavy enough. Now, the interesting thing is on the left-hand side, on the right-hand side, sorry, where I have this, I denoted here with a dash line, that is a spin-dependent wall. What does it do? It is transparent when the spin is up z, and it is totally reflective when the spin is down z. So that's all. So depending on how I prepare the spin of the particle either will see this wall or will not see the wall. Okay. So, for example, what would be a Hamiltonian for this? Well, you have the kinetic term, P over 2m. Then you have the potential on the left-hand side, which is like, you know, an infinite potential step on the left-hand side that just describes this totally reflecting wall. I will have a delta function in the middle. And on the right-hand side, well, on the right-hand side, I have a very high potential, VR, but it is multiplied by 1 minus sigma z. So when the spin is up z, this term is 0, and the wall is totally transparent. When this is minus 1, this whole term is 1, and the particle sees the potential and will be reflected. But in my case, I start with a spin up z. So the particle does not see that wall. Okay, one thing that is important in this situation is the fact that sigma z is a constant of motion. you see, none of these terms, the kinetic term or the wall on the left or the partition in the middle, they are independent on the spin. The only place that depends on the spin is this wall, but the potential depends on sigma z. So sigma z up is a constant. Okay. So what happens in this situation? Well, this is strange. There is some delay in between what I do and what appears on your screen. That's interesting. I haven't encountered that before. Let's see. So here there are a few snapshots. I start with a particle in this corner of the box. The particle comes, hits the partition and comes back. This is the instance when it's coming back. And a very small wave packet propagates on the other side. After that, the particle continues its way, collides with the wall on the left, while this little wave packet just continues and leaves the box. And the particle continues to go back and forth here on the left-hand side. Each time it emits a wave packet. And you see the first one emitted goes further away. Then I have another one, closer. If I look at the amplitude of these wave packets, the first one has an amplitude epsilon, which is the amplitude for transmission through this middle partition. And the other ones have even smaller amplitudes. Why? There is still the epsilon at the partition, but the wave packet on the left-hand side becomes smaller as it continues to emit tiny wave packets. Now, let me look at the part of the wave function that is out here. So that is, of course, a superposition of all these wave packets that have been emitted. But the important thing is, what is the magnitude of this thing? So the magnitude, let me look at the scalar product psi out with itself. Well, let me look at all these terms. They are orthogonal on each other because each of them represents a wave packet in a different place. So if I look at the scalar product, it's simply the sum of the absolute value square of the coefficients. Each coefficient, the largest one, which corresponds to the first emitted wave packet, is epsilon. The other are smaller. And I would look after n collision, where n is in fact the number that I took here in the magnitude of the transmittance. So in that case, what do I have? Well, I have n terms, so n, and each term is equal or smaller to epsilon squared. So it is n pi square over n squared. So the upshot is that it is a term in 1 over n. So if I take the partition in the middle to be very, very reflective, in a time of order n, the entire wave packet that goes out is basically zero. The particle remains for the time of interest, which are n collision, remains in the left side of the box. Okay, so far so good. Now, here is the main question. You see, I started with my particle up z and having this funny spin-dependent wall. But for up z, this spin-dependent wall is basically inexistent. So the question is, can I just replace this arrangement by something where there is no spin-dependent wall at all? Okay, that is the main question we put. And to our surprise, we will find that that is not the case, that there exists a dramatic difference in between this situation and that situation. Okay, let's see what happens. So what I would like first is just to compute the Heisenberg equation of motion for other spin components when the particle is in this state up z. And in particular, I'm interested to know what happens with the sigma x component. Okay. Now, I can go ahead and actually compute the Heisenberg equation of motion, knowing what the Hamiltonian is, and so on. But there is a simpler way of doing it. I will compute the Heisenberg equation just by going back to Schrödinger and see how to interpret it. So what I would like to do, I would like to see also, just as a preparing exercise, what happens if the spin is down z. Okay, that's a mathematical exercise. My spin is actually up z, but for a computation purpose, I would like to see what happens with down z. Okay, so if I were to start on the left-hand side with my spin down z, then remember, that means that this wall here is totally reflective. So when this wall here is totally reflective, what happens? Well, this is very much like a two-state system, particle on the left or particle on the right, with a little bit of transition probability between them. So what happens is that after some time, which is actually of the order of n, the particle moves from the left completely to the right. And after n over 2 more steps, it comes back here. Now, pay attention, this is overall time of order n. So while if the spin would have been up z, it would remain all the time on the left side. If the spin is down z, it transitions to the right and comes back. Now, the important thing that I would like to draw your attention is the fact that by the time the particle goes back to the left-hand side, it acquires a minus sign. So it started in the state left, and it now ends in minus left. Well, you know that pretty clearly, because when you have a spin half particle, say I put it in x direction, and I would like to move it like a two-state system, then by the time it makes a 2 pi rotation, it acquires a phase of -1. One can check the mathematics pretty easily. I'm not going to go through it, but that is the main element, is the fact that the particle, if it is with a spin down z, by the time that it makes the transition to the right and comes back, it comes back with left, with the minus sign. So now I can use this thing in order to see what is happening if I start with sigma x. Now recall, sigma x is a superposition of up z and down z. So I have to superpose what happens in this situation with what happens if I start in that situation. So after n steps, if I started with up z, I remain in the same state. But if I started with down z, I come back with a minus sign. So the particle is in the left side of the box, but if I'm superposing these two things, and I have up z plus down z, here I will have up z minus down z, which means if I start with left and the spin in the x direction, after n steps, I get with a spin left and with x in the opposite direction. So the spin x changes. Now, here is the trick. I didn't start with a spin in the x direction. I start with my spin in up z direction. So the particle stays in the left side of the box for the entire time. That computation that I made for what happens with the x, that just tells me what are the Heisenberg equation of motion for the sigma x observable. And what the Heisenberg equation of motion tells me is that despite the fact that the particle is all the time in the left-hand side, the sigma x operator changes. It changes from plus x to minus x. Or by the same token, if I would have started with minus x, it will go to plus x. So that is what the Heisenberg equation of motion tells me, because it tells how the projectors on plus x and minus x change. Okay, but this is just a computation. This has no observable effect for the time being. The particle is up z, stays all the time up z, only I computed what happens with this sigma x. Before going forward, here is the paradox. And what is the paradox? I have this box, the long box. My particle started in the x, in the left side, and all the time it bounces there. It will leak eventually out, but that is time of n squared. But for time n, it just stays in the left-hand side of the box. The only place, however, where there is a magnetic field is in the wall of the box on the right. You see, the particle stays here. The magnet, sorry, if I have it with up z, the particle always stays here, but the only place where the magnetic field is there. So here is the paradox. How can a particle that is in this location, in the left-hand side, know about the existence of the magnetic field in a very remote wall? Now, the distance can be immense between these two things. This is a Gedanken experiment, but you can always imagine that it is an enormously long box. So there is no magnetic field, no leakage of the magnetic field from the wall on the right into the left-hand side of the box. Nevertheless, the Heisenberg equation of motion tells me that because I have a magnetic field here, the x component, sigma x, is changing. Okay. Well, that is, of course, just a computation. But already there is the paradox, because something is going wrong. The particle never gets to the region of the magnetic field, yet the Heisenberg equation tells me that the spin is changing. Now, to take this seriously, one would like to have some observational effect, not only to make a mathematical calculation, because then one can say, well, I ignore the Heisenberg equation of motion. So what I would like to do? Well, I would like to start with my particle in the left-hand side of the box and with a spin up z, but I would like immediately to measure what the spin is in the x direction. Remember, it's the spin in the x direction that the Heisenberg equation of motion tells me that it goes from this to that. Now, if I were to measure it strongly, then I would completely destroy my initial state, which was up z. it will be either plus x or minus x, and we'll have a component that will leave the box and go away. So that's why I would like to measure the spin x weakly. Now, I let the experiment proceed, and at the end of the day, I measure the spin also in the x direction. So what do I expect to see in this situation? You see, the Heisenberg equation of motion told me that during this entire time, the spin in the x direction moved from this to that. Or if it were to start here, it will move to the opposite. So depending on what I see here, I just measured sigma x. If I post-select the cases with sigma x positive, then I actually find my weak measurements show that initially the spin in the x direction was negative. So it shows me that there is this flip from negative to positive. Also, sometimes I may get sigma x in the other direction. So I do the other post-selection, and I find at the post-selected state sigma x to be minus, and the sigma x weak initially in that situation turned out to be plus. So already I have now an observational effect, not only a computational one. So people were, okay, let me first, probably in this audience, I will not need to describe what the von Neumann measurement is and how this weak measurement occurs. But let me do it in case not everybody knows that. The standard way to describe a measurement is to imagine that I have a system, and here is the state of my system, and I have a pointer. Q is the pointer. And the pointer initially, just if you imagine an old-fashioned measuring device, the pointer has to point to some zero value, and then the pointer will move. So here is my pointer, is in a Gaussian around Q equals 0, but that would be a non-normalizable state, so I take a Gaussian with some spread delta. The interaction Hamiltonian, if I want to measure some arbitrary operator A, goes like this. First of all, I have a coupling constant, delta of t, which tells me that I want to turn on and off the measurement at time 0. It is proportional to the observable I want to measure, and it is also proportional to the conjugate momentum to the position of the pointer Q. What does this do? Well, the unitary operator associated with this Hamiltonian is simply, I take the Hamiltonian integrate, which is nothing else than integrating the delta function. So it is e to the IA times the momentum of the measuring device. So if in particular, I take my state of the system to be an eigenstate of A, the effect of this interaction, if I apply unitary, when A acts on an eigenstate, just gives the value of the eigenstate. But if you look here, e to the IAP, that is nothing else than the shift operator, which will shift the value of the pointer. So the state, if my system was in an eigenstate of A, it commutes with interaction Hamiltonian, so it remains in that thing, but the pointer is shifted by the eigenvalue A. If, on the other hand, I start with some arbitrary state psi, I can decompose that in eigenstates of A, the observable that I want to measure, and then the pointer will be in a superposition of shifted position with these coefficients. So that means here are two different versions. An ordinary strong measurement is one in which the pointer is pretty well localized. When what I mean pretty well localized is that the spread, the uncertainty of the initial value of the pointer is much smaller than the shifts the pointer makes when it indicates the different eigenvalues. So seeing the pointer here, I will know for sure that I'm in the state A2. On the other hand, the weak measurement is something where the value of the pointer is very spread. Well, the uncertainty, the initial uncertainty of the pointer is very spread out. And then as the pointer shifts, the states are not orthogonal and cannot be distinguished by each other. Now, the interesting thing happens when I do the weak measurement and apply a post-selection at the end. So this is the initial state of my system and measuring device. This is the interaction, well, the unitary, and I make a post-selection of my system. In our particular case, I started with a system in the state left and up Z. I want to measure perhaps the spin in the X direction, and this is the final state that I would like to post-select. Perhaps in this simplified situation, there is no evolution. If there is some evolution, I would update my final state. So it turns out that in such a situation, the pointer actually moves around some number A weak that has this formula, meaning A weak is psi A phi over psi phi, which is a number that differs from the eigenvalues of A, and in fact can be much larger than the largest eigenvalue or much smaller than the smallest eigenvalue, can even be a complex number. I will not go through the theory of deriving that thing. I'm very happy to do that if there are some questions. But let me go now and see what the results will be. All I will do is I will apply this formula, psi A phi over psi phi. So here is what I would like to do as for my first measurement. In my first case, I want to start my system left with a spin up Z. So this is the state. And immediately I want to measure sigma X weakly. Then I would like to let the system evolve for n steps and measure sigma X again. So let me remind you, the formula was, I look at psi, the measured thing, phi over psi phi, where psi and phi are the states at the time when I perform the measurement. In this case, I would have to see what is the state, the final state here at that time. So in principle, I should update this formula if there are some evolution, psi u1, u2, psi over u2, u1, psi. That would be the basic formula. Here it is u2, and here I have just identity. I measure it immediately. So my initial state is L up Z, and then I want to measure the operator sigma X. I let the system evolve for un, where u is just one single bounce in the box, and then post-select of finding it in the left-hand side and finding it with a spin up z. And this is divided just by the initial state and the final state propagated back in time. Okay, now you see immediately what happens here, because the first thing is that sigma x will flip sigma z down, will be down sigma z, but I will, and then I will apply the time evolution. Now, I should have put, in fact, I see a mistake, u n times there. Now, what happens mathematically when I flip the spin down z? Now it sees the wall at the other end. So by now it has, after it evolves, it can go back. We know what happens. It went to the right side, it goes back, but it acquires a phase of -1. So the upshot is that the entire weak value is -1. That tells me that if finally I post-selected on situations in which sigma z is up, the weak value of sigma x initially was -1. Now, I can also post-select on sigma x being down, and you would find out that here the value is +1. So by making the weak measurement here this is the time as it evolves. So making the weak measurement immediately after the preparation shows me what was the spin there. If I wouldn't do the post-selection, I wouldn't know anything, because of course, when the particle is prepared up z, it's equally likely the spin in the x direction to be plus and minus x. Only when I compare, when I do the correlation with what I see, finally, I can see that the spin has flipped. Okay, so now we really have an effect. There is no magnetic field in the box, yet I see that the spin in the left-hand side changed. Now, before going and continuing to this, let me address some other issue. You see, if I start with a spin up z, then really I will not have any measurement to tell me that what was the spin in the x direction initially. If I do not disturb it at all, then I know that in case I find it here in the left side finally, even those very small wave packets that went here, they couldn't come back from the wall on this side, because the wall is totally transparent to it. So if there is any wave packet that went, it will just run away. But if I measure sigma x, then a claim is, well, then I disturb and the system is no longer up z, but may flip a little bit to down, and then it may bounce back from the wall and see the magnetic field there. Well, but that sort of criticism will miss the fact that even when I just computed what happens with the Heisenberg component, when I did not do any disturbance, when the spin is strictly up z, I already saw that sigma x flips. And this measurement is weak. I disturb it as little as I do, as I want, and just will tell me what the spin was. It will confirm the validity of the Heisenberg equation of motion. Okay, but now come further things. Let's try to understand the idea. So in the box, inside this big box, there is no magnetic field at all inside the box. The only magnetic field is on the right. So then inside the box, also sigma x must be conserved. Any component of the spin must be conserved. The only place where they can change is when they hit the wall on the right-hand side. On the other hand, I see that the particle remains here on the left-hand side, but the spin in the x direction changes. So somehow the spin in the x direction must leak out. Okay. The question is, how does it leak out? So now let's focus at intermediate times. You see, here I have the wave packet, my particle, that went there a few times, and now it is just coming back up to that position. And I have here one wave packet that was sent out, and there will be other wave packets further out to the right. Okay, yes, here and so on. So the first question is, these tiny wave packets that I dismissed, I said they are of order 1 over n, even the sum of all of them. Will I not, if I would just try to perform a measurement in the position where, in the location where there is this wave packet, in the transient, will I not see a particle there? Well, obviously, even if I make a strong measurement here, if I find it here, it will continue out and I will never see it in the left-hand side. The fact that it's in the left-hand side means that I will never find at an intermediate measurement the particle being there. The same is even if I measure this projector weakly. You see, I want to start with left up z, let it evolve up to some intermediate time, measure the projector where in the location where I know that this tiny wave packet may be, and let them evolve up to the final time and post-select the fact that I find a particle here with a spin up x. Now we see immediately this is 0 because nothing here flips the spin in the z direction, and I know what the time evolution does to when the spin is in the z direction. Just pushes this wave packet outside. So this entire thing tells me if I try to measure in this, of course, if I try to measure whether there is a particle in some other location, I will just get 0 even from this side, sorry, even from this side of the equation. But if I measure on the location where I know this little wave packet is, even then the result of the weak measurement is 0. But now here is a crazy thing. I don't want to measure whether a particle is there. I want to measure whether the spin is there. So what I want to measure whether there exists a spin at that location. That means I want to measure the observable, which is the projector in the right-hand side of the box in this region, times sigma x. That is what I would like. I want to find, not is there a particle here, but is there spin x there? Well, the weak measurement shows me that the weak value of the spin is different from 0, and mathematically comes from the fact that although I started up z, when I apply the spin x, up z goes into a down z, and down z is reflected by the back and has non-zero overlap here. That is mathematical. So what it means is that I have now a situation in which my particle moves all the time here. If I try to see, is a particle in this side, in the right-hand side, I find no particle. If I ask if there is a spin, I find yes, there is a spin. So the particle stays all the time on the left-hand side. There is a flux of spin. I can measure the spin, and I can see the spin propagating. I see no particle if I measure. And even more, after each bounce, I see the spin propagating, moving out. Then there is another bounce, there is another wave packet of spin that moves. And there is another wave packet of spin that it moves. And in the end, if I look how much spin it went in this flux, well, it went exactly the difference sigma x equal -1 to sigma x equal +1. Or the opposite, from +1 to -1, depending on how I find this final spin. So we see a flux of spin that is going. The magnetic field is here, so somehow the image is that the particle remains there at all times, but the magnetic field on the right-hand side attracts the spin towards it. The spin, there is a flux of spin propagating from my particle out there. And you can even see the beginning of a sort of counterfactual communication, in the sense that you imagine that you have somebody here, you have Bob here, that would like to communicate to Alice that is over there. And what Bob can do, he can decide when he wants to transmit a 0 or a 1, he would decide to either insert this spin-dependent wall or not insert the spin-dependent wall. Alice, who is on the other side, can do the weak measurement and see whether the spin in the x direction has changed or not. And there is no particle traveling between them. Of course, as a mean of counterfactual communication, this is not very useful, because since Bob needs to do weak measurements, he needs to repeat this experiment many times with Bob. But there are, this entire issue of counterfactual communication, if that is the only part that one is interested, has evolved, and there are far more complicated and more efficient schemes. What is important here, however, is to see, in all these counterfactual communication things, the main paradox was there is no particle. How do you define there is no particle? Perhaps if you would make a weak measurement or whatever. Well, here we know, even if I make a weak measurement, I never see any particle going from Alice to Bob. However, what it goes is the fact that Bob can control some degree of freedom, which in this case is spin. So in this particular counterfactual communication, the actual degree of freedom that is the one that Bob controls in order to send messages to Alice, that one propagates. So the paradox of counterfactual communication, which said that, well, particles don't go, is now you can think of it in a different way. You say, look, I don't care about the particles, because particles are not the things that Bob uses in this particular instance to communicate to Alice. Bob uses spin in this particular experiment. So the spin should go, even if the particle doesn't. This is the main. Now, of course, once you have this, you can start playing, and there are many interesting things that you can do. But I guess that my time comes up to the end, and I just want to let you with the idea that there is a new type of non-local effect. This is just the tip of an iceberg, and there are a lot of interesting experiments, but mostly interesting conceptual problems one can ask about this. But for today, that's it. Thank you. Thank you.
Fantastic.
Okay, any questions?
Yes, any questions?
Any questions if there are? Yes.
Sandu?
Ah,
Do you
hi
hear
there.
me?
Yes, I can. Yes.
I don't know if you,
Yeah.
of course, I don't know if you like the opposition, but I think you know that I cannot do anything else.
Opposition is always welcome. Yes.
So again, I think this Cheshire Cat is very interesting story.
Yes.
And the fact that you can separate different degrees of freedom, and in one place it interacts with 1 degree of freedom, another interacts with another degree of freedom, it's really surprising and interesting.
Yes.
But you know that I don't buy the whole philosophy. I have my definition where was a particle. The particle was where it left a trace. And so any local interaction, if the weak value of any local interaction is not 0, then it left a trace. In fact, I consider something not so different in my first paper on past of the particle. I have Mach-Zehnder interferometer, and it's particle with a spin, which I send it up. In one arm, I flip it to down, and I post-select only up. Then, if I ask in which arm it is, and look on weak value of projection, or try to measure without the spin degree of freedom, it can be found only on one arm. But if I look on spin, I will find it in both arms.
Or you may find it only in the other arm.
And there is another version that I can find only in the other. This is not the fact. The important thing I can find there is a spin trace in a place where there is no particle, according to Yakir's and your kind of way of thinking. There is no charge, there is no mass. Any coupling to charge and mass will give 0. But if you do couple to a spin, then you see. And since I believe in there are all kinds of local interactions, so there is a coupling. So there is some trace left. So you cannot say the particle was not there. So it's not counterfactual. So this is.
Okay. So what is the question?
But just a sec. So this is just a comment about semantics. Maybe another comment is that you use Heisenberg, which, you know, I don't like Heisenberg. Schrödinger is good enough. And you had this case that you have this particle, you start up Z, it go up, down, whatever, then you make post-selection and up or down X. And you say, oh, it's interesting. Then in the beginning, it was weakly up X. Now, and then you apply Heisenberg at whatever and say that it's very strange. The particle never was near magnetic field. But if you consider Schrödinger picture, there is a forward evolving wave function which you considered well, and you describe completely. But there is also a backward evolving wave function. You don't need even the weak measurement. You maybe need it to find out what's going on in the beginning of X. You have post-selection down X. So you have to look on this backward evolving wave function. If you look backward in time, you'll see it was in a region of magnetic field. So there is no any kind of big miracle. The forward evolving wave function was, didn't see it, it was Z and whatever. But the backward evolving wave function was in the magnetic field. So this explains why the weak value of spin, whatever it is.
Well, okay, so let me try to formulate some questions out of all this. First of all, there is a very, what has happened? Shall I stop sharing? Okay. Suddenly the sharing just dropped. Look, the point is like this. There is a story that is consistent mathematically. So I don't think that we have any dispute about the mathematical facts in the story. The question is what the interpretation is. Now, the interesting thing about an interpretation is whether it is useful. First of all, the story is new. So these are effects which are very strange effects about a measurement. And what is essential here is that it allows you, first of all, to see other things that and ask other questions that you would have not thought if you would not have this particular way of thinking. So let me give you an example. Here it's an example. Let me try to share again my screen to see if it is possible. Okay. So here is one type of question you may have. Let me see. So here is again the famous box. Here is the famous box. And here I have the...
Maybe it takes some time. I see white.
Maybe it takes some time. I don't know. Probably that's why the... okay.
Okay.
It's coming. I don't think that this has anything to do with Einstein's relativity, unless the photons bounce back and forth in one of the cavity, maybe my house, or they don't enter in your cavity or whatever. Here is an interesting question. Suppose you have this particle here. Now, here is something interesting. If this particle is up Z, then I know that during any time of order n, the particle remains in the left side of the box. On the other hand, if the particle were to be down Z, after time n/2, the particle would be there. Okay. So any time of order n, so let me take n/2. So that means that if I start with my particle here, with some spin in some direction, whatever that direction is, and I perform a measurement whether the particle is here or not at the time n/2, that is a measurement of sigma Z. Yes? Because if the particle is not here, the spin was up Z. If the particle is here, the spin was down Z. Okay? So now the question comes like this. Suppose you start with it up Z. So now you wait n/2, the particle is there, and now you perform a strong measurement on whether the particle is here. Okay? You will not find it there. Now the question is, what has happened with the correlation between sigma x initial and sigma x at a final time? Can you tell me immediately?
This is not. If
No,
you want
can
to
you,
play,
no. Can you tell me? Here comes, and here,
you ask
attention.
about you ask
Can
about
you-
operator, which I'm not interested.
I
I'm
don't
interested
care
in the
whether
wave
you are
function,
interested.
which gives me the whole story. The correlation between
Lev.
sigma x now and sigma x later. Ask about correlate about operators, and then you need Heisenberg picture. If I don't want operators, I don't need Heisenberg picture. The wave, if I directly connect my experience just to the wave function, then I don't need to ask these questions. I agree with you that if I want to ask this question, I need Heisenberg picture. And this is very useful.
Okay, so tell me immediately what happens with the correlation. Here's a question. Here it's really a question that is important. Can you tell immediately what happens with the correlation? If I send a pulse here, a strong pulse, a strong laser pulse, what happens with the correlation between sigma
Again,
sigma
the correlation, it's not, you can ask what maybe is the value of some operator. Or,
your question.
No, ask me about,
look, you may not.
What?
Okay. You perform a weak measurement of sigma x here, and you compare the correlation between the answer here with the final state. What has happened?
I think you analyzed it before. You said, I don't remember it. What if it's makes a whole flip or the half flip, and then you can know what happened. So I don't say that your analysis is not good. What I claim that everything can be done with Schrödinger picture too.
Lev, everything can be done with Schrödinger picture because we are not out of quantum mechanics. So that is a triviality that everything can be done with Schrödinger picture. The question is, first of all, is it useful? So first of all, there is an interesting experiment that nobody knew it before. Whether you like it from the prism of counterfactual or not, that's a different thing. The main idea is that there exists this dynamic Cheshire Cat, which is a true effect that is there to stay no matter how you interpret it.
Yes, again, we do not disagree about mathematics and effects. We agree about language. So I can be with my local language and refuse to say that there is any kind of non-locality here.
Nobody could ever force you to accept a language, but nobody can force me to not to use it, and I will use if it is useful.
Okay, I'm going to assert the chairman's privilege here to stop this discussion. Lev, time out. We're going to go on like this forever if I don't stop you now. Let's let other people have a chance to talk with Sandu as well. Are there other questions or comments from everyone else in the audience?
But thank you, Lev, for waking us up. This is so exciting. Thank you.
So maybe I ask a question. Spencer has a question.
So yeah, there's this slide with the spin flux, and I'm wondering, is there a way to kind of sum the spin flux over the times that the particle is in the middle, and to kind of add them up to build up this X spin change that you're getting?
Yes, so the idea is the following here. Oh, I'm very glad to see that somebody is using a mask. I will go to a conference myself and intend to do the same thing. Okay, so look, doing weak measurements, in fact, at the same time, you can perform many of them simultaneously. That's the whole point. So you can also check what is happening here, what is happening here, what is happening in all these locations at any time. So being weak, they do not disturb each other. So what you will see, at some time, you see that the spin is here. At a later time, you see that the spin is here. time you see it here. At a later time, you see it there. At a later time, you see it up there. And then it starts again. It starts here, moves there, moves there, moves there. So you see this entire propagation. Furthermore, if you see quantitatively how many there were, because with every single bounce of this particle, you generate another propagating spin without particle. And if you add how much spin it is precisely the difference that accounts to this sigma x. So yeah, in that sense, it's really a flux that you will see if you make the measurement. You will see it clicking at various locations.
Okay, other questions? So Sandu, I'm interested why you call it Dynamical Cheshire Cat, because if I think about the original Cheshire Cat with the interferometer, there is still motion of particles going into this interferometer, and you're still measuring these different observables. So why do you distinguish this as a dynamical effect as opposed to the original?
Well, in the first place, it is because it really has has an interaction. The other one, it was by itself. I just showed that there is a Cheshire Cat effect, but I didn't let that property, the smile, to interact with other things. Here, the smile really interacts with a magnetic field there.
Okay. And then I guess my other question would be
the propagation. Okay. Yes.
Yeah. So a follow-up question. It seems like this would be a relatively easy experiment to do with optics. Have you thought about this? If I replace
yes, obviously, this thing can be done with Mach Zenders, with a chain of Mach Zenders, one after the other, or an optical cavity.
Optical cavity. Yeah.
Yes. Probably it depends on what your type of experiments are. Probably the optical cavity is the simplest one. I would be thrilled to see it. That definitely is the case. So one would have, instead of this spin dependent, you will have a polarizer that closes the cavity at the other end, and so on.
That's right, but you want a reflecting polarizer though. A standard polarizer would absorb the alternative, and you want it to reflect. Right?
Yes, I would imagine that coupling probably two polarizing beam splitters one after the other, you may make something to reverse it back and basically make like a reflective thing. I would imagine that is possible to make some sort of arrangement that will bounce back one polarization and let go another.
Okay.
Yeah, I never thought how to do it, but I can't imagine it's a theoretical scheme for that.
Okay, any other questions from our audience? Okay, then let's thank Sandu again for the nice talk.
Thank you.
I hope to see you soon. Thanks again.
Well, I'm looking forward very much for the time when I'm starting now to travel a little bit more locally, but I really hope to be able to come soon.
Okay.
Okay. Good.
Bye.
Thank you so much, son. Bye.
Bye.
Thank you.
Bye. 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 Bye.